Next speaker is Miguel del Alamo, and he'll be speaking on multiscale bounded variation regularization. Miguel?
Yeah, thank you. So first, I'd like to thank the last organizing standing for organizing this nice workshop, and this week has been great. So many interesting talks. So my contribution to the workshop will be the topic of my PhD. So it's to work with my PhD advisor Axel, and also with a former PhD student of his, Housen Li. And it is it's nice that I'm talking after Sarah, because this has a lot to do with some work she did very long ago, so around 20 years ago. And it's also different to the total variation that she talked about a moment ago, because this is what I'm going to talk about. It's about nonparametric regression, or also application to inverse problems. So we want to estimate a function itself. So let me begin with a little motivation. Let's begin with an easy motivation of denoising. So the beamer is not great, but here you have an original image and some Gaussian noise on top of it. And it's actually very bad. The effect of the noise is, of course, that you are losing some of the locally constant, or some of the locally constant pieces of the images. And what is already a good tool, or a well-established tool for denoising, is this total variation regularization, as Sarah talked about. So in that case, if you are given data, noisy data y, which would be the image on the right, this total variation denoisation would be the minimizer of an L2 penalty. So you are much in the proximity to the data, the L2 penalty, and also regularizing with this L1 norm of the gradient. So this L1 norm has the effect in the last of encouraging sparsity, and if you require a sparsity on the gradient, you're basically requiring that your reconstruction is piecewise constant, doesn't vary much. And as always in this kind of Lagrange multiplier problems, you have a free parameter, lambda, called here, that you have to choose somehow. And you are free to choose this however you want, but this is going to play the role of the trade-off between how much you regularize and how close to the data you are. One way of choosing this lambda would be, since in this case we know the ground truth, f, we could choose the lambda that minimizes the L2 error. And here is the reconstruction that you get in that case. The beamer is very bad, but you also see that the reconstruction is not very good. So in this case, lambda is being chosen very small. And hence, this penalty term doesn't play a big role, and that's why you don't get rid of much of the noise. No. There are many other ways of choosing this lambda. For instance, another general way of choosing it would be to minimize another functional. So let me write what this is. This is actually the Bregman divergence, or symmetrized Bregman divergence of the total variation semi-norm. And you will see in a moment why this gives a much more locally constant reconstruction, because in the continuous case, this divergence between two functions would be the same as the difference of their gradients times the difference of their, just the direction of their gradients. Wait, this is absolute value. So this is, that's how you come at this equation, and moving the terms around a little, this turns out to be the same as the sum of the absolute value of the gradients at each point times a more geometric term that somehow measures how these two gradients are aligned with each other. So in order you are trying to minimize this divergence between the two functions, and this is going to be small either when the two gradients are 0 or very small, that means where both functions are constant, or where both gradients are well aligned, so that these two terms are almost parallel, and this term vanishes too. So that means somehow that here you are requiring the reconstruction to be constant on the pieces where the true function is constant, and also to have jumps, or to be parallel to the jumps where the function has jumps. So here close to the building. But
It's not a distance, right?
this is not a distance.
Is it
I
a
mean,
problem? It's not.
No, I mean, no, you just have to minimize this. In order to minimize
It's a
it,
problem from the point of view of what comes out of it.
no. I mean, in which, what are you thinking of? Do you have a particular...
Well, for example, you know, it's enough for f and g to be both constant but different, for this divergence to be zero.
Exactly.
Does it not translate into any problems in the reconstruction, potentially?
That could be. They're constant but difference. That could be, but you see, in that case, this term would be big, typically, right? So you are given a reconstruction.
It's negative, right? I mean, because you have Cauchy-Schwarz there,
And this is
always
smaller
non-negative.
one. Mm-hmm.
and it's zero if f is equal to g.
But not only.
No, not always. So you're saying if they are off by a constant, this is still zero.
Not because it takes
Mm-hmm.
yeah, okay.
But yeah, that's a good point. I mean, in this I'm using just to choose the parameter, this lambda, and that's for the reconstruction. It should be
I'm just
okay.
trying to think if you can game it so that it's horrible because it's not this.
Mm-hmm. That could be. I mean, I'm just presenting this result to argue that it's not good. So then it's okay.
Oh,
It's not good.
It's not good. So what is happening here, and you see it, well, you see it, so is that this lambda is not going to be too large if you choose it by this objective rule, sort of, and you are putting too much weight on this regularizing term, and you are doing a great job in reconstructing these locally constant pieces here. But these, what you would call smaller scales of the stairs up there, they are you miss them totally, right? Because you regularize too much. And I mean, well, maybe to put it in a nutshell, what a way of seeing it is that since you are choosing a parameter lambda to match at the same time the proximity to the data and the regularization, but this, I mean, there's going to be an equilibrium, but the two extremes that you have is that either you keep all the scales but too much noise, or you lose some of this information in the small scales and you have a good job in the big scale. But well, the point is that it's difficult to have a good choice for this parameter lambda that works well everywhere. And in general, what this motivation would be about, we'll say that we want to have some estimator that combines the good properties of this total variation regularization of being a very constant reconstruction here, but also adapts to the different scales of the problem, of performing well here, but also performing well here when you have this little structure. And then the conclusion of what I'm saying now, and this doesn't look so bad, and what I want to present is a type of estimators, or some family of estimators that sort of do this, in that here is how one of these estimators perform. They sort of get this locally constant reconstruction on the big scales, but on the small ones they still, well, work not great. They miss something, but it works well too. And this estimator is defined this way, so I'm not telling you what this multiscale constraint is, so we'll get to that in a moment. But the point of this is that in this example, at least, and I'm going to argue that this is a general phenomenon, this estimator has the good points of both two regularized estimators, so that they are constant, and two, well, looking and keeping information in the small scales. And, well, keyword here would be this is be helpful to getting some spatial adaptation in this image denoising problems. So this was supposed to be a motivation, and now what I'm going to talk about is first argue what are good or sensitive multiscale constraints, then present a theory for these estimators, for which I will also show that it attains the optimal convergence rates in image denoising, but also in higher dimensions. So this is a more general theory. It will also work for inverse problems. And finally, we'll show you some more pictures showing how it performs in simulations, and also in some applications in microscopy. So about this first part with the penalty, let's see, to keep it just conceptually high level, I think of this dichotomy as using a global penalty like you do with the L2 norm, in which you measure the distance from your estimator to the residuals globally. So you sort of look at the difference at every point and put them all together with the L2 norm. And as opposed to that, you can think of a sort of local penalty in which you look at portions of the image separately, and these portions of the image separately will be these little boxes that I'm writing here. You could do other things. So this is this sort of local rectangles about which Bodhi talked on Monday. There are other possibilities of doing local penalization. But here, so the idea would be that by looking just at local patches of the picture and requiring that you are close to the data in these local patches, you get rid of, well, how would you put it? You are not overwhelmed by the noise everywhere in the image, right? So, and you are able to concentrate on, here you would say, in this spot, the picture is locally constant, then you can just approximate everything by a constant, and that's great. In this other spot here, there is more structure, and then by looking closely at every point, you can adapt better to what is actually there. And in more mathematical terms, what such an norm could be is if you take the set calligraphic V to be a set of such rectangles in 2 dimensions, you could take the observations Y and subtract your candidate function, average them over such a cube. There is some weight factor here that is chosen so that everything matches properly. And then you look at the maximum of all these local contributions, or local deviations, if you want, from your residuals. And, well, again, the message here, or the idea here, is that this looking locally at the picture is gonna gives you a chance of being locally adaptive to the different regularities of the function. So this is about the penalty that I'm going to use, but let me take a step back and think about this function estimation, let's say in the denoising case, because if we want to work with these variational estimators, there are at least 3 possibilities of defining such estimators. So we already said I want to have a total variation penalty term and some data fidelity term that measures the deviation from the data. But now we could be looking at this typical penalized estimation where you minimize a combination of both functionals, in which case you have to choose lambda. Or you could say, I want to minimize the distance to the data under a constraint on the smoothness of the function. I don't want my function to have too many jumps here. Or you could say, I want to minimize the jumps of the function by not being too far away from the data. And, well, and some weak conditions on the data fidelity here. These estimators are going to be equivalent, but the point is, in each one, you have to choose these parameters. And, well, that is the issue, sort of. And, of course, there are also choices of the parameters so that asymptotically everything is okay. But in the real world, you are not always in the asymptotic case, and so then there will be a difference on which parameter you choose. And the observation now is that this third minimization problem is, from the statistical point of view, it makes sense to use it because under some assumptions, let's say, on this data fidelity term, so if it would behave like the functional L would be a function of the difference Y minus the candidate G, you see, you could determine this function gamma, or this value gamma, out of the distribution of the noise only. So here I repeated the model we're considering. Observations are function plus noise. And in this case, you have a chance of determining the function just depending on the noise. So in particular, you don't need any information on the true function f in order to determine it. So you don't have to assume, like you would have to assume in this case, your function f has total variation norm equal to this, and then you can estimate well. And, well, by using this estimation method, I will show you in a moment the theory, you also get a chance of being adaptive to the true structure of the function. So either the function is of total variation, is locally constant or locally linear, you can adapt to that too, and don't have to put prior information on it. Okay, so if we decide we want to estimate this way, the estimator I'm considering has this form. So again, given observations that, let's say for simplicity, they are IID normal, the estimator I'm considering is the minimizer of this total variation semi-norm, or the L1 norm of the gradient, under, again, this same multiscale constraint. Now what I want to give you is yet another, maybe more statistical interpretation of this multiscale constraint which maybe you already heard about it. Also in body stock there was this Samson underlying, which is that there is, in the case of Gaussian noise, this turns out to be a sort of combination of hypothesis testing problems, in the sense that if you get yourself, let me go one, if you get yourself a candidate function g, and you want to match in each of these local boxes b whether your observations are compatible with this candidate function, so you want to test this hypothesis, your observations in the cube b come from this candidate function f, then what the likelihood ratio test would do is to look at the average of the observations in the cube. That's what you're doing here. And if this average is too large, that means your data deviates too much from the candidate function, and then this candidate function is most likely not the true regression function, so you reject this hypothesis. Now you can play this game for each of the cubes that you have here, and if you would test all these hypotheses simultaneously and take into account all the different, possible, in a sense, they could be correlated. Oh, jumped. All these tests could be correlated because the boxes could overlap. But if you test all these hypotheses simultaneously, one test statistic for doing so would be to take the maximum of all these statistics and rejecting this intersection hypothesis if this is too large.
Can I just make a quick comment?
Sure.
Would you mind going back to the slide where you had this nice duality?
Mm-hmm.
This one. So to me, basically, the top way is like the lasso, and the bottom way is like the Danzig selector.
Exactly. There is, yeah. I mean, like the lasso. This would be the lasso, right?
Well, yes, but then if people want to represent lasso in a subject two way, then they usually choose the top way of saying it. So basically, minimize the square distance between the estimator and the data, subject to the L1 norm of the parameters being less than something. Whereas in the Danzig selector,
you are doing this
convergence around, saying, choose the smallest, choose the simplest estimator in the L1 sense, the smallest L1 norm, subject to the residuals still looking like
exactly.
Like
so
residuals.
describing the data well. Yes.
Yeah.
So exactly. So the Danzig selector is was a sort of good motivation for this kind of estimation.
Did you say it and I missed it, or did you?
I didn't say it. No. I will talk about some references in a moment. So I was,
Right.
yeah.
Okay.
But also in the references I given, I'm not talking about the Danzig selector. So it's yeah.
Thank you.
Where were we? Yes. So in this multiple hypothesis testing business, and that, in a sense, the fact that this is a possible multiple test for testing all these local hypotheses gives another, if you want, motivation, but also an interpretation of the estimator, because then the constraint here would be to say that whatever candidate function g you are considering for the minimization, it has to pass all these local tests. And also another good thing of this issue is that, you have here this 1 over square root of that's the cardinality of the set B, so you have to weight them, all these local averages, properly, so that they are all matching. What I wanted to say now is that in the case of Gaussian noise, let's say you have a natural candidate for this regularization parameter gamma. So since you are taking the maximum of cardinality of B normal random variables here, and neglecting all the possible dependencies that are between them, this choice, or this scaling at least, of gamma is a good candidate for the estimator, for this gamma. And in that sense, you have already determined all the parameters in this estimator. So you will see later also in the theory that there is a precise choice for this gamma. I'm being sloppy here. Okay, have something else. Okay, so we can get now to the little literature review, which is also very partial. So this is, I just want to make a point, sort of, I don't be exhaustive at all. So about the first block of references I want to talk about are the ones dealing with this total variation penalties, and there is of course the paper by Sarah and also a paper by Donoghue and Johnston, and in both cases you are dealing with the estimation of functions of bounded variation in one dimension, and both results essentially show that either with TV regularization with the proper lambda or wavelet thresholding both do the job and perform optimally for estimating these functions. Then there is, well, in the last years there have been many works on working with the discrete counterpart of this total variation problem. So you want to estimate a vector on a graph. So we put a vector on a graph, also requiring that it doesn't vary a lot. And we saw the talk, for instance, by Rebecca on Wednesday, and well, many other works in that direction. And also, it's interesting that there is a generalization of this total variation basis, which you require that not the first derivative, but let's say the second or the third derivative has a small L1 norm. In that sense, for instance, in the second derivative, you would be requiring that the function is piecewise linear, and that, well, I mean, it also has many applications, of course, with that is relevant. And for instance, Body worked on it recently. The point that I want to make here is that, of course, what I'm doing is more similar to these first two references, and the issue is that there is no, not that I'm aware of, other theory for these continuous total variation problems in dimension larger than 2. And to my knowledge, that is the case because these functions of bounded variation, well, of course, there are many possible ways of defining what a function of bounded variation is in higher dimensions, and the functions turn out to be very badly behaved. So they are, if you want a way of imagining it, they are at the boundary between differentiability and non-differentiability at all. So since they can have jumps, then you cannot infer local properties well from nearby behavior. That makes the analysis very difficult. Okay, but this was regarding this total variation part of the problem, and also this other multiscale part of the problem. There are also many references here I'm not mentioning. So I believe the first paper using these multiscale penalties for nonparametric regression was the one by Nemirovsky, where he used precisely this local average penalty. And well, there were also the famous paper by Duncan and Spokoji that Body talked about on Monday, using this penalty for testing, and other approaches like this paper by Davis and Kovacs, combining in one dimension total variation and this local data fidelity term. So giving this taught strings algorithm, it also works very nicely in 1D and more work. And there are also some empirical works like these three I'm mentioning here that combine a total variation penalty with what I would call now some multiscale constraint. Either, let's say, on these cubes is what I presented before, but you could also do it using the curvelet coefficients of the residuals, requiring that they are small, or the wavelet coefficients. And from this, there is this nice paper of Candes, where they just do empirics, but it's very nice. So he makes good points of why these estimators are good and how they perform too. So the point that I want to make with this second block is that these estimators perform well in practice, but they also turn out to be quite difficult to analyze in practice. So there is no theory for them. I'm talking about this second part, right? On the upper line, there is some theory. And also the conclusion now is that in what I'm going to present in this talk is some theory for this kind of estimators, so combining multiscale with total variation. And the analysis is so that it works also in higher dimensions. So in particular, we can deal with images. Now, let's go to the theory. And for that, for simplicity here, I will consider that the observations that I have are given from this white noise model. And typically the way I think of this white noise model is always you have some dictionary there, which you can think of as a wavelet basis, for instance, and you project this white noise model to this wavelet basis, or some dictionary in general, phi. And then your observations are, at the end of the day, this y omega. Omega is the index I use to index this dictionary. And these are essentially the coefficients of the true regression function f with respect to this basis, or this dictionary, plus noise. And since we are in this white noise model, they turn out to be correlating in normals. So maybe for illustration, what I will think of here is that this dictionary phi could be the wavelet basis. That's the well, easiest to think of. Maybe it could only be some localizing indicator functions of cubes. So this could take us back to the situation I described at the beginning with local averages. And it performs very well in practice to this curvelet frame, so what Emmanuel Candice proposed. And well, I don't want to get that much in the details, but here is a little reminder if you don't recall what these curvelets are. So they were proposed by Candice and Donoho, and they were trying to get a counterpart of wavelets that approximate well functions locally, but in 2 dimensions. So in 2 dimensions, many wavelet constructions perform very badly. And in particular, what they wanted to describe well are contours in images. And for that, these wavelets are defined by some rotation and anisotropic scaling, so that, as you see here, the form, they get more elongated in one direction, and that's why they are well suited for describing, well, jumps along contours or in general 2-dimensional images. But, well, this is not so important. So the point is we have a dictionary that describes and helps us to describe the image locally, and that's what we observe in these observations. Now, in this more precise model, given these observations, the estimator I'm considering is this one. So now I'm putting the notation at this right. So I said that the true regression function is of bounded variation, meaning, well, functions with jumps. The proper definition is that the weak derivative or the weak gradient of the function is a finite radon measure, and the mass, the total mass of this measure, is denoted by this FBV. So that is what you call the total variation semi-norm. And our estimator now is in a sense minimizing this total variation semi-norm under a constraint, and now, well, it's the constraint that the residuals projected to this dictionary are properly small. Now, well, essentially I'm repeating the story that I told you before. We can choose this threshold gamma n as being some small quantile of the noise here. And why is that? Because you see, if you insert the observations y here, up here, and well, what I was saying, for instance, is that you take g to be equal to the true regression f. What remains here is the maximum of all the just projected normals. So if you choose gamma to be such a quantity of that statistic, you are guaranteeing that the noise, well, or that the true function sort of satisfies this constraint, but not much more, right? So there are not much many functions satisfying this constraint. And, well, in that sense, if you were in the normal case, so this is the threshold we would have. And I don't know how much time. As I was arguing, you're choosing the threshold gamma n so that the true regression function is in the constraint set, and by definition then of the estimator, you have with that high probability that your true estimator has a smaller total variation semi-norm than the true function, because it is the minimizer on the constraint set of there, right? And this is helpful in the proofs, but it is also helpful in conceptually, because it means you are not building extra jumps in the function, right? So you are not getting more overfitting the function. So that would be the idea. Yeah.
So your epsilon omegas are independent, or
what's it then?
The epsilon omega, the noise term, the discrete.
No, not necessarily, because they arise in this way, right? And then if these functions phi omega would be orthogonal to each other, then they could be independent.
Yeah, then yes, but in this case you're
not necessarily. No, I'm not assuming that.
Okay.
Yeah.
But when it comes to your choice of gamma n, is it somehow playing a role at all, or the dependence, the degree of dependence among these things?
Actually, I don't consider it. No, I take the threshold in the independent case, which is larger than the threshold in the other, because if they get correlated, the maximum gets smaller, and that's how, let's say, more conservative. Yeah, I mean, since you know the dictionary, you could go on to model this dependency and put it in.
Okay.
Whether it's worth it, I don't know.
By working with in the bounded variation space, for example, with images, are you giving yourself unnecessary trouble in the sense that, for example, natural images, are they understood to be, only of bounded variation, or are they more regular than that?
Yeah, that's a good point. I mean, there is also the definition of a natural image, so I'm not sure.
Well, take a typical range of images that is useful for, I don't know, autonomous vehicles, other aspects of computer vision,
Well,
medical imaging?
you know, I think there are many interesting images where you want to have this jump structure, right, and preserve it. So think, for instance, in many tomography.
But I understand, but having a jump structure does mean, you know, your function is in the boundary variation space, but it often also means even more regularity.
Yeah, I mean that's a good point. So would it do to consider just the L1 norm of the gradient there? That's the point, sort of.
Right.
You
know,
I mean, at the end you discretize the problem and you solve it as if it was just the L1 norm of the gradient. So then, from the computational point of view, it's the same.
So I remember when people talk about, you know, Besov spaces in the context of wavelets, then there was some empirical work trying to determine Besov parameters for typical natural images. And I wonder if there was anything similar. Obviously, a boundary variation space doesn't have a parameter, but I was wondering if there was anything similar.
Who worked on that, you said?
Oh, I don't remember who. It was 20 years.
Because there is, I mean, I'm also not talking that much about it, but the machinery, I mean, do we get to the proof here? Wait. The machinery behind all this work, it relies a lot on wavelet coefficients of functions of bounded variation and Besov regularity and so on. So that is the machinery behind it. And yeah, it makes a difference there to work. You complicate yourself a lot with working with bounded variation, but it works. So. Okay, so this is, if you want now, the statement of the estimator, and the convergence result that I prove is the following. So here is, if you want a more precise choice of the regularized parameter gamma n. You have oh, I don't know whether I wrote. Well, this sigma should be the standard deviation of the data. I don't know if I wrote it in the slide before. You know, all these parameters here, and this kappa is a number larger than this other number. You can compute this explicitly, but it's messy. So it depends on the dictionary file that you use. And what I'm saying is that the expected LQ error of the estimator to the truth, and LQ is in some range of Qs, it goes to 0 with this polynomial rating n and some polylogarithmic factors uniformly over a parameter set, and this parameter set is defined by a constraint on the bounded variation seminorm, as it makes sense. But also, you need some constraint on the supremum norm. So, since the functions are so badly behaved, just imposing a constraint on the bounded variation seminorm doesn't guarantee that you are bounded. And well, if you are not bounded, everything is very messy. So you have to put this assumption by hand there. And there are also some assumptions on the dictionary file that I'm going to discuss in the next slide. But what I will show also in the slide after the next is that this rate of convergence turns out to be optimal up to this, you know, these polylogarithmic factors. So optimal in this class, right? Over this set. And now the assumptions on phi that gets kind of technical and it's getting late too, so maybe I go kind of fast through it. So there is the natural assumption that these elements have to be normalized, and this has to do with all the Gaussian errors that you have having the same variance. So that's a assumption is okay, and the others get more complex. So let me tell you, we have some examples of dictionaries satisfying this. So let's think of the wavelet basis, which is the easiest one of to illustrate these assumptions. So what I'm saying is that we pick a subset of the index coefficients here, m, which you may think of as, let's say, the wavelet coefficients up to some resolution level. So j goes up to the log of m, and then what you want is that the derivatives of the elements there, they don't have to grow too fast. So you require that the maximum of the derivative of the elements up to this resolution level, it has to grow polynomially in m. So this is not too big guy. So as a little illustration, if you think of wavelets, and here you have these hard wavelets in 3 different scales. So the one, and then you shrink the support by 2 and get higher by 2. And so on. So this, if you look at dictionaries with this wavelet-like structure, would you shrink and shrink the support and resize, these guys do the job here. So they have such a balanced growth as you go down the scale, and that's what you need for the dictionary file. And there is then this next assumption, going back to this Besov regularity, which starts to be the right measure of regularity in these spaces. And what this assumption here is telling you is that, well, there is the norm of this Besov space. Let's take it as a norm of some space. And you can bound it by the combination of two terms, which are in a sense balancing each other by saying here you approximate, or you are bounded with the coefficients of your function g with respect to the dictionary. And the more coefficients you get, so the larger this set would be, the smaller this second term should be. So this is, in a sense, kind of an approximation error that you're making by knowing these coefficients only. Again, in the case of wavelets, if you know about these things, it is very easy to show that this assumption holds because you have characterization of these Besov spaces by a wavelet, and that's all fine. Now, what we will work with is with combination of dictionaries with wavelets and curvelets to have this directionality. And for them, you can also show that this holds. And kind of more complicated, but it also works is with this local averaging kernels. That's, well, it's kind of a lot of work to show that this, well, the first one is okay, the second assumption holds, but you can do it. Now, I wanted to say something about the proof, but if you're interested, you can ask and we talk about it. Otherwise, it's going to get late. So maybe the summary of what I just said and the theorem is that the theorem gives you this rate of convergence in the white noise model, and here is, well, a kind of little and sloppy argument of why these rates are actually optimal. So you have that these functions of bounded variation contain the functions in the Sobolev space W101 with such bounds on the norm. And for this, you know, for instance, there are many papers, the one by De Leon and Juditsky, that the rate over this space of convergence with respect to the Q loss is of this order. So you look at the polynomial order is matching with the one that we have for our estimator here, which gives the optimality over there up to log factors. But there is something interesting, namely that if you look at the regression model, which is, I mean, I always think of this white noise model as a kind of theoretical way of not dealing with discretization problems. If you look at the regression model, which is more intuitive, and you say you scan the values of the function at each point, there is a discretization error coming in, and this comes in part because of the functions of bounded variation being so irregular, and if you know the behavior of them in a neighborhood, you just know the behavior near to that point up to a big error, so it can jump a lot. And so there is this discretization error coming in that slows down the rate. It is so this the first term in the minimum is the same as above, and it dominates in dimensions 1 and 2, which gives you the minimax optimality there as well. But in higher dimensions, the error gets larger and dominates the convergence rate. And maybe the first thing you can think of is that, well, this is just in a sense an artifact of the proof. So I'm dealing with this discretization error in a very rough way. Maybe there are smarter ways of dealing with it and not getting this slowdown. But there are some recent results, for instance, what Richard Samworth talked about on Monday, that in other functions classes, I mean, and this is not a very nice comparison because he works on by estimating vectors and with respect to the discrete risk and so on. But the results there are that by estimating monotone functions that are bounded on a bounded graph, you also have this kind of different behavior of the minimax risk in dimensions 1 and 2, and after 3 you get a slower rate, which is different as different as what you get here. But well, so this suggests, for instance, if this is the minimax rate over this case, and the monotone bounded functions are also of bounded variation, it tells you that the minimax rates in dimensions larger than 3 are not the ones as before, so they don't scale like this. They may be, well, scale like this, or they may be slower, because the class we are considering is larger. So this is, yeah, I still don't know what is optimal here and how we are doing. So, yeah.
So, are you sure about that inclusion? So, because in monotone functions beyond one dimension, there is anti-chain, and you can take any value in the anti-chain. If you take any value in the anti-chain, I'm not sure, is it always contained in the bounded variation?
In the bounded variation. That's a good point, but I'm playing here with the fact that I require that the functions are bounded in L infinity, and also Richard needed it to be bounded.
But in the anti-chain, they can just take any value at any.
You mean that you could building many jumps there so that you are not of bounded variation anymore?
But I don't know, I'm just asking you.
That's a good point, but I think it should be okay because you are of bounded variation on a compact domain, so you cannot just go wild.
Okay, we can talk.
Yeah, that's a good point. I hadn't thought of that, of playing in the anti-chain direction. Maybe that's true. Okay, nevertheless, so what I wanted to point out here is that in this regression model, the story is not finished yet, so we don't know what is happening in larger dimensions. But let me get now to some little pictures and simulations, so we will be done in a moment. I had this slide explaining the computation of the estimator, and maybe the take-home message is that although the estimator looks awful because you have the constraint set is this maximum over many different sets, there are many ways of computing it. For instance, Richard also talked about this Dijkstra algorithm for projecting to sets. So if you look at this constraint closely, it turns out to be a complex constraint, and this is actually the intersection of many half spaces. So this is a linear constraint in G, and this is essentially saying G has to be in this half space, and then the other term in the maximum set has to be in the other half space. And so this constraint set, or to ensure that a function is in the constraint set, you can just project it there. And by playing with this Dijkstra projection algorithm and then minimization on the other part, you can compute it. There are faster ways of computing it with the Samboy-Pock algorithm, but yeah, let's not get into that much now. So here you have the not very surprising result. It's very similar to the one I saw at the beginning. What is it?
How long does it take with your implementation?
So right now I'm using a MATLAB code that is very, very slow, and it takes about 15 minutes to compute a 512 by 512 image. So it's highly unoptimized.
Right, but which one of these? So are you using the? Okay.
I'm using the Samboy-Pock. Yeah. So in a sense, what you do is you replace this constraint by a hard constraint. You're saying you minimize the bounded variation seminorm plus the indicator function of this set. So you get a hard constraint or a weighted indicator function.
Right.
And then, so since this is not differentiable anymore because you have the indicator function, you have to do something else. And there is where the Samboy-Pock comes in, because then you alternatively solve this problem and also look at the dual minimization problem and solve it there. And they have, well, this alternative algorithm of solving one and the other that works when you cannot differentiate, right? So you cannot do some.
And if you increase the image size by 2, how much slower? How does it scale?
So to be honest, I haven't tried it for larger images. I tried it for smaller, and then it gets much faster. But I'm not sure. Yeah, I mean, I'm playing with this at the moment just as a toy. So I haven't done the effort of programming it in C, for instance, and it should get much faster. So back to the images. I mean, this is not very surprising what you get here. So zooming in one part, you see that we have the original noise image. Again, for instance, this Bregman divergence choice of the parameter and the constraint that you see in the big scales of estimators and doing well, and the small ones, you get what you want in this case. You can play with lambda, of course, and interpolate well around in the L2 penalty case. It's more funny to look at this crazy image here of the vertical pattern, and well, zooming in what in that region, you have the same result, but it's difficult to see anything. So again, if you zoom in the other part, and you see some more what is happening. So here, because of the different frequencies of spacing of the vertical lines, the estimators get sort of confused, because well, there's, for instance, this region where the vertical lines are more spaced, and for instance, well, if you take some cuts here on the sides, you see that it's difficult for the estimators to work well. For instance, in this L2, somehow thinks that the signal is higher there because of the smaller frequency than on the close by point. But otherwise, they are doing. If you look at the big scales, both as you expect, they are doing a good job. So here, where there are more space, you get a nice reconstruction and get rid of much of the noise, which would be the point. And yeah, well, you have a similar picture up here. So here it's more difficult because the lines get more space too. So now I had an application.
Someone to tease you, they would say that the noisy version looks pretty good already.
Yeah, I mean, if you want all the little structure, the noisy version is good. Yeah, by getting rid of the noise, you get rid of the small structures.
Yeah.
Yeah. I mean, and the point in a sense is getting rid of the noise and not of the small structures, right? But I mean, you are right. Here you see everything you want to see. Yeah. So, I mean, a way to compare it would be to look at these other. There are many measures, of course, of whether reconstruction is good. And I'm not giving the one from the noisy version, but there is. Yeah. So I have this microscopy application, microscopy data, based on this fluorescence microscopy results, because we are working in Göttingen with the gentleman here in the middle, works on these fluorescence microscopy problems, and so it's. I mean, if you are interested, I can explain it to you. Otherwise, we can go to the conclusion directly. So how are you feeling? I mean, it has been a long week and very, very intense. So I don't know.
We have 13 minutes. Go ahead.
Good. So the point with this fluorescence microscopy problem, so with this super resolved fluorescence microscopy that they got the Nobel Prize awarded for, is in typical optical microscopy, you have the problem of not being able to resolve very small structures just by the physical limitation of the wavelength of the waves that you use being too large. So you cannot resolve much smaller structures than the wavelength of the light that you use. And if you want to use optical light, which is good, I mean, or usually you can just take X-rays, which have very small frequency to resolve very small structures. But if you use it in living tissues, for instance, you just kill whatever is there. So it's not a good thing to do. And what this gentleman came up with was a way of using visible light for microscopy, but getting a much smaller resolution. Actually, an arbitrary small resolution you can get with this problem without being too invasive to the probe that you're using. And how they work is by using fluorescence molecules. So I would have liked to put a picture of how these molecules look like, but I didn't find any good one. So these molecules are kind of, or some of them, the ones I've worked with, they are sort of like little barrels, and they can have different ways of bending themselves, in a sense. And the important thing is that they can have, in the simplest case, let's say, they can have two configurations. They can have a ground state, which I call here the off state, where they just do nothing, so they are folded in a weird way so that they cannot do anything. But the fun thing is that there is a certain excitation pulse, so there is an excitation frequency, and the colors here, they are not random, so there is a certain frequency of light at which if you activate them, they fold themselves in a different way, and there they are in this on state in which they can emit fluorescence, so photons of a certain frequency. Now, these fluorophores were known for long, and one way of profiting of them would be to, if you say you have this chain of whatever tissue you want to have with fluorophores attached to it, you can go and throw light on them of the right excitation frequency so that they get activated, and in this activation state they can emit fluorophores, which then if you record, you can sort of say, okay, well, here in the middle there is a higher density of fluorophores, which maybe they attach to certain structures of cells or tissues, which allows you to see what they are. Again, here you may have a problem that if there are many fluorophores close to each other, you cannot resolve well which is which, because they are emitting all at the same time. And then one of the techniques of getting better resolution there is to selectively activate the fluorophores, and this is what this step technique does, which is you activate in a region with this confocal microscopy beam, but then using some, well, complicated physics, optics mechanisms, you manage to send a deactivation beam, so a beam with the frequency that sort of drives the molecules down to the off state in this ring-like region around the point, so that only the molecules in the middle remain active, and then only this, well, what is written here in red, only these molecules are going to emit, giving you a much more resolved image. Now, this is a very high-level image of what is happening. It's, of course, very complicated, and the optics that allow you to have such precise reconstructions, they are very complicated, but yeah, that's what we can think of. And from a mathematical point of view, the emission of these molecules can be well represented by, for instance, Poisson random variables or negative binomials. So a simple model would be to say, if this F denotes the density of fluorophores in the probe that you have, what you observe is the convolution of F with respect to some blurring kernel that comes from the optics, so this you know typically, and a Poisson random variable drawn from this side. And well, what you can see here is some typical images of what you have. This is the first type of microscopic confocal, so you see that the resolution is not great. So this is a proof from this pimentin, well, not really protein. So this is a similar. So this is one of the components of the skeleton of the cells that they hold the cell together, but they also are involved in the, for example, in the cell division process, where the cytoskeleton rearranges itself and splits itself in two. And well, here you have this. It's written there the raw data and the L2 penalized, or the TV penalized L2 estimator, taking this kernel into account. So in principle, we don't have theory for that, but you can estimate it well. And this is what you will get using this multiscale estimator as presented with this kernel, taking it into account, and using local boxes. So here, actually, it would be much better to use curvelets because you have this very strong directional structure, but we haven't done it yet. There is a big difference if you see now. That was the confocal microscopy data. If you look at this state microscopy data, you get, of course, a much better resolution. And as you can see, the comparison here. And of course, you can go then and say, okay, let's apply the estimator to this confocal microscopy data to further denoise them. I mean, they're already very little noisy, but you could wait. You could try to do that, and that is what you get here. So this is still. You can play a lot with the different parameters and get a less noisy image. The point is that you can, well, you isolate the local features of the individual lines of this cytoskeleton, and that is, well, in further steps, the physicists would use that to characterize better cell division and so on. So this, yeah. Well, let's get finished. It's really late. And what I wanted to say is, in a sense, that this in nonparametric regression, this local adaptation problem can be achieved by these multiscale penalties. And the other take-home message is that the combination of total variation with these penalties well, can be computed. We haven't talked about that, but it works well in practice. And importantly, at least in a white noise model, we have the theory proving that is actually optimal. And well, many things that I didn't talk about was how to prove these things. So this relies a lot on interpolation theory and harmonic analysis, but this is, well, the talk would have been much more messy. And it has a strong relation with this family of norms that Ifmeyer proposed also to measure texture on signals. So it was more in the image processing community and also in harmonic analysis. So this is a weird connection between this local testing and multiscale testing problem and the thing that Meyer proposed. And there is finally extension to inverse problem, which is very relevant because in many applications you work with that. And in a sense, the only thing you would have to do is to take other dictionaries that is sort of adapted to the operator. But well, maybe if I give another talk in half a year, I'll tell you about that. No, thank you.
We have some time for a few questions.
What's happening with these adapted dictionaries? How do they work roughly?
Well, I'm using the word adapted, and what I mean is they have to be adapted to the operator that you have the inverse problem with.
To the operator.
Exactly.
I see. Okay.
And that is the reason for that is kind of obvious. If you think you have a blurring operator, then and you know that the function, the underlying function is locally constant, but the operator is blurring, so you see it makes no sense to go to the blurred data and put a locally constant guy. Yeah. Yes.
So when you motivated the talk, you said that if there is a constant stretch, you would expect this method to do very well. Then you would expect this method to do very well if, for example, the function is just a constant function.
I see where you're going. You're talking about the adaptation to more smooth structures.
Or do you have any such results which goes beyond the worst case rate, as I would?
Yeah, that's a good point. So I don't have such results. No. In a sense, it's clear where to go in the proof and see where to modify things, but technically it will be tricky because I mean, it's easy. You will have to say, okay, if I know that the function is constant, then I can estimate it better and improve this term here, the other term there. So I believe that it holds like the results that you got in the trend filtering, that you can also make profit of this structure. But the proof will be tricky because it's a little different to the discrete case. Yeah.
I was wondering about the statement you results. You have an n, which is getting large, and there's xi's here. So are you thinking about infill with relative to these images, or?
I don't get the question.
Well, you have the result, but for n large, you have these bounds and stuff. So you think about n getting large.
Yeah.
And how does that relate to the xi's, especially relative to the images?
To the xi's? Oh, you mean the sample points?
Yeah.
Yeah, that's a good point. So actually, I have to say that I wrote the L large. Actually, you have a very quantitative expression for n, and it is not an asymptotic result. So you have n has to be larger. It has to do with the norm of the function. So if the function can be too large, then you need n to be large enough in order to sample it properly everywhere. And yeah, I mean, in the case of images, you would require in a sense to sample it very finely, so to have a very small discretization error or pixel size. I mean,
yeah, but so in your model, you're thinking you have yi equals f of xi plus epsilon I. And so these xi's are supposed to be these pixels.
Yes.
I assume in the image, and then you're not thinking about n. And then I thought was be the number of pixels. So right, you're thinking about n large. Are you thinking about the sense about n getting larger? In which case,
you have to sample the image finer, sort of. Yeah. I mean. Yeah, that's in these settings where you have a microscopic probe or an image, it's weird to think of asymptotics, right? Because you don't know whether you have to zoom in a lot or you have to get more data from the sides.
Whether it was infill or some sort of.
Yeah, so typically I think the bounds are quantitative, so you say n has to be larger than 300, for instance, right? If you put in some numbers inside, then you could say if the images are sampled fine enough, then you are good. If they are not, then you are still making a big error.
Look at those images where you have the epsilon i's, or in the discrete case, you have my ID. Why not have them be some sort of have dependence in the spatial?
Yeah,
it seems like there's a playoff. There's a trade-off here about smoothness of the function versus what you could model through the noise.
That's a good point. So I mean, regarding the correlations of the noise, which in many applications they are going to be there, right? In these microscopy applications, you scan the image linearly, and then it plays a role what happened before, what you are seeing now. And I mean, probably the biggest point regarding the noise is the assumption that it's Gaussian. So this you can relax it very easily to sub-Gaussian, but also you can play some tricks to get it Poisson. Maybe that's more interesting to look at other noise problems and also to put the correlations there.
Not so much about the distribution, but the dependence between neighboring pixels.
Yeah. So maybe this is similar to the question before about what happens if the noise were correlated. Then this choice of the parameter gamma that I told, I chose it as if they were all independent, and if they are dependent, actually the maximum of these random variables gets smaller. In case they are Gaussian, right? And in which case the choice of gamma is still good, it's just too conservative. It's a little complex to explain it there, but I think in the case they are very correlated, you are doing good, just you maybe lose some parts of the function by regularizing too much. Yeah, I mean, but a proper modeling there, it might be possible, but it's probably, well, it would depend from situation to situation, I guess. A modeling of the correlation and how you have to adapt to it.
Okay.
Yeah.
I have another question. If I have 2 minutes. So in the multiscale statistic that you looked at, you did not look at a penalization term. Can you comment on the advantages, disadvantages of using any penalization term, for example?
So there is this paper I mentioned, which you also mentioned, that's from Göttingen and Goettingen, where they use this kind of statistics for testing. And in testing, you want to have typical, you want to have the minimal results, and the test has to be very fine. And the statistic as it is, so if you remember, you can go back. If you remember the statistic I wrote, it diverges like the square root of n, of the number of terms. And this is in a sense the term that you subtract in the domain spokojnie test. So are we good here or no?
In particular, do you think that can improve some of the log factors?
Exactly. So the effect would be in the log factors. What you are losing here is so this is exactly the point. You choose this gamma to be divergent. So okay, it's here. You choose it to be divergent, and it's actually weird. So I missed a square in factor. So this is the proper gamma. This divergence, and if you subtract this term, you would get, so some of the log here's come from these logs here. So you could get rid of them. There are not also, there are other logs popping in from other probably artifacts of the proof. But so I think the way I think of it is that for estimation,
more difficult to subtract off a term and then do it.
So one problem that you could have is that this term here could no longer be a semi-norm, because as it is now, it is the maximum of the Weber's coefficient or something. This is a semi-norm. If you subtract this constant term, it will no longer be that, and it will make part of the analysis difficult. The analysis that you do afterwards in order to get this kind of result, right? That would be difficult. And what else did I want to say?
It's a good stopping point, so we don't show change data.
Good. Thank you.
You can continue this outside. Okay, let's thank both speakers in the session. We convene at 11:30.